Let x1, x2 to x of 2023 be pairwise distinct real numbers. They are all positive. A of n is defined to be the root of the sum of n real numbers x1, x2 to all the way to x of n times the sum of their reciprocals. It is also known that A of n is an integer for all n. Prove that A of 2023 is greater than or equal to 3034. In this problem, x1, x2 to x of 2023 are positive distinct real numbers. But they are not arbitrary. They are chosen so that this square root is an integer for all n. An observation. The sequence an is strictly increasing because from one term to the next, we are adding positive values in the square root. a1 equals 1, and a2 is strictly greater than a1, therefore a2 is at least 2, a3 is at least 3, and so on. So A of 2023 must be greater than or equal to 2023. However, the target is to prove A of 2023 is greater than or equal to 3034. The speed of increasing is faster. Claim A of 2k is greater than or equal to 3k for all positive k. If this is true, then A of 2022 is greater than 3033 for k equals 1011. And therefore, A of 2023 is strictly greater than 3033. Then it is at least 3034, and we are done. The claim can be proved using mathematical induction. And mathematical induction contains two steps, a base step and an inductive step. For base step, we prove the case for k equals 1, meaning a2 is greater than or equal to 3. a2 equals the root of x1 plus x2 times 1 divided by x1 plus 1 over x2. Expand the multiplications, we have four terms, x1 divided by x1, x1 divided by x2, x2 divided by x1, and x2 divided by x2, which is 2 plus x1 over x2 plus x2 over x1. Using arithmetic-mean-geometric-mean inequality, we can prove that x1 divided by x2 plus x2 over x1 is strictly greater than 2. I will explain it in detail right away. Then a2 is strictly greater than 2, then a2 is at least 3. This concludes the step 1, the base step. The arithmetic-mean-geometric-mean inequality tells that if A and B are positive numbers, then their arithmetic mean A plus B divided by 2 is greater than or equal to their geometric mean, root of AB. Moreover, the equality holds only if A equals B. In other words, if A and B are distinct, then the arithmetic mean is strictly greater than the geometric mean. Now, let's look at x1 over x2 plus x2 over x1. The sum of these two fractions is greater than or equal to 2 times the geometric mean of the two fractions, which is equal to 2 times 1, that is 2. However, we know x1 and x2 are distinct. Therefore, x1 over x2 and x2 over x1 are different. As a result, the sum of these two fractions is actually strictly greater than 2. For the inductive step, we are going to prove a of 2 times k plus 1 is greater than or equal to a2k plus 3. Then, as we know, a2 is greater than or equal to 3, and a4 is greater than or equal to a2 plus 3, that is 3 plus 3, which is 6, and a6 is greater than or equal to a4 plus 3, that is 9, and so on. Eventually, we have a2k is greater than or equal to 3k. The index 2 times k plus 1 is simply 2k plus 2. So a of 2k plus 1 is equal to root of x1 plus x2 plus all the way to x of 2k plus 2 times the sum of the reciprocals of these 2k plus 2 terms. The objective is to prove this square root is greater than or equal to 2k, a of 2k plus 3. Let p equals x1 plus x2 plus all the way to x2k. These are the sum of the first 2k terms in the square root, and leave the last two terms in red alone. Similarly, q is defined to be 1 over x1 plus 1 over x2 plus all the way to 1 over x2k, the first 2k terms of the second factors. Then a of 2k plus 1 is the root of p plus x of 2k plus 1 plus x of 2k plus 2 times q times 1 over x 2k plus 1 plus 1 over x 2k plus 2. Now, we have a root of 3 terms in sum times the sum of another 3 terms. Expand the multiplication, we have 9 terms. These 9 terms seem messy, but the simplification of the expression is actually straightforward. First, PQ equals x1 plus x2 plus all the way to x2k times 1 over x1 plus 1 over x2 plus all the way to 1 over x2k. We know a2k is simply the square root of this production. Therefore, PQ is just a2k squared. Secondly, we look at 4 red fractions. 1, 2, 3, 4 here. They are x2k plus 1 divided by x2k plus 1, x2k plus 1 divided by x2k plus 2, and the reciprocal, and also x2k plus 1, 2k plus 2 divided by x2k plus 2. It is equal to 2 plus a fraction plus the reciprocal. As we discussed in the base step, we know this quantity is strictly greater than 2 plus 2, that is 4. There are 4 terms remain. They are separated into 2 groups. First, p divided by x 2k plus 1 plus x of 2k plus 1 times q. This term and this term, this and this. Using AMGM inequality, it is greater than or equal to 2 times the geometric mean of these two quantities. And x of 2k plus 1 cancel out, we end up with 2 times root of pq. We know pq this is simply 2 times a2k. Similarly, the rest two terms sum up greater than or equal to 2 times a2k as well. Put everything together. A 2 times k plus 1 is strictly greater than root of a2k squared, that is pq, plus 2a2k plus another 2a2k plus 4. This is actually a perfect square inside the square root. We end up with a2k plus 2. So a of 2 times k plus 1 is strictly greater than a2k plus 2. Therefore, a of 2 times k plus 1 is greater than or equal to a2k plus 3 as desired. It can be proved in a similar manner that a of 2k plus 1 is greater than or equal to 3k plus 1. This was actually my original plan because when we plug in k equals 1011, we got exactly a of 2023 is greater than or equal to 3034. If we combine the result for even and odd indexes, we have A1, A3, A5 greater than or equal to 1, 4, 7, and so on, and A2, A4, A6 is greater than or equal to 3, 6, 9, and so on. These inequalities are actually optimal, meaning we can construct the sequence that is exactly 1, 3, 4, 6, 7, 9, and all the way to 3034. Thank you for watching.